Good afternoon and welcome to the sixth problem solving session of the course Fundamentals of Semiconductor Devices NOC 24EE02 hosted by NPTEL. This is March 2 for the week 6 of this problem solving session series. My name is Amit and I am a PhD student at ISA Bangalore. Just a quick summary of what we had talked about in the last five sessions. In first session we talked about that we can classify the materials based on their electrical conductivity given by the symbol sigma as metals, insulators and semiconductors. But we saw the peculiar thing about semiconductors is that their electrical conductivity can vary depending on certain factors known as doping, and we saw that it can exhibit a wide range of electrical conductivity, and that's why they're a very versatile material, and many devices can be made out of them. The word semi we explained in the essence that why there's a band gap in a semiconductor, which would mean something like this, that let's say this is the conduction band boundary and this is the valence band boundary. This means there are electronic states below EV in the valence band, the electrons can reside there, and similarly above conduction band electrons can reside. However, this gap that we see, which is also known as the energy band gap or EG, is the forbidden gap. This means no electronic state exists and thus an electron cannot reside here. And the reason for the origin of this band gap we saw was that when a large number of atoms of, let's say, a semiconductor material like silicon, they are brought together, they're in close proximity, what then happens is that their orbitals tend to overlap and they start forming bands, right? Bands is essentially a continuum of energy states, and that's what we had seen in the first session. And we also saw that an electron can jump from, let's say, conduction band to valence band, and it can emit a photon, or vice versa. We can excite an electron from the edge of valence band to conduction band by shining some light. So this will give away some light, and if we shine some light, some photon of sufficient energy, it can be excited. And we also model that, please remember, these electrons that are there in conduction band and so on, they are residing in a lattice. So there is a lattice made up of semiconductor material, and we saw that their potential can be modeled using something called the Ronick-Penny model, and it's a periodic potential, and this is potential versus position x. And in this position, this is essentially some quantum mechanical features. We can solve this problem, and what we got was something called an EK diagram. So E is your energy and K is your wave vector, which is 2 pi by lambda. And this, when we represent this same, this is E versus X. In this diagram, this is E versus electronic energy versus X. Here it's E versus K, and we can represent the conduction band and valence band here as well. So this is the conduction band, let's say, and this is the valence band. So again, this is the band gap that we see, EG, similar to in the real space. This is also known as reciprocal space. And E versus K is the band structure, and this curvature over here that we're seeing in the conduction band, which can be used to give the effective mass. This is a very handy tool in the sense that we can now just kind of sideline the quantum mechanics and just apply all our classical mechanics like F equal to ma and so on, and other expressions that we know from the Newtonian mechanics. Finally, we talked a bit about the Fermi function. I'll come to that, but there's something called the Fermi direct statistics, which is followed by fermions. So fermions are essentially your particles with half spin, like plus half, minus half, plus 3 by 2, and so on. And we also saw that there are energy levels, which I said hinted over here, that there are some energy levels. They are so close space that it looks like a band, and the degeneracy essentially means there are multiple states available in the same energy level. And we also discussed in a Fermi function, which is given something like this. Fermi function is nothing but the probability. It's a probability distribution function, the probability of occupying a given energy state. So if energy state, let's say this one, what is the probability of occupying that electron is here? And we saw that it was given by 1 plus exponent of E, the energy we are concerned about, minus EF over KT. It had an exponential dependence over the am I audible? Can someone confirm, please?
Yes, sir.
Okay, fine. Thank you. Okay, so as you can see, if the energy goes above EF, E greater than EF, let's say, or E equal to F, you can see it will be exactly half. So that's the definition of a Fermi level. And when energies are greater than EF, so what you can see, this exponential will be larger than 1, and thus the probability will be smaller than half. And we had discussed this in quite a bit detail. Finally, we talked about the density of states. Density of states in a 3D system, which is given by this function, density of states. We saw that it goes as square root of energy, right? And these are essentially defining that how many energy states are here in this, in let's say this conduction band. How are they distributed, these bands, and similarly over here, what's the distribution, right? And finally, we obtain the total carrier concentration. Let's say the electronic concentration I'm only concerned. Similarly, you can write for holes. So electronic concentration, let's say from EC to infinity, because that's where we are concerned about. So holes, it is essentially nothing but an absence of electron, which we say residing in the valence band. So which we see that if you integrate this, the density of states, that means how many energy states are available, times the probability of occupation of those states, you integrate that, you got the total amount of electrons that are available. You can similarly write the expression for holes, right? So this is what is in an intrinsic semiconductor, which means inherently there are some electrons at any given temperature. This is for intrinsic. But what we can do is we can change this concentration. We can alter this concentration. How? We can dope them. So if we dope it donor type, that means these entities, donors, will have an energy very close to the conduction band, somewhere over here. And thus even at 100 Kelvin, many of the electrons can now jump, and thus the concentration of electron increases. Similarly, there is another type of materials called the acceptors, so which denoted in green over here. So if let's say some electron is in the valence band, they can simply jump over here, and now these holes that are left behind in the valence band, they can contribute to the current. We also saw that these donors need not always get ionized. They need a certain temperature, like above 100 Kelvin or something. So that's that. Based on this understanding, then we saw what is the Ohm's law in the semiconductor world, so to speak, or even the electronics world. We are habitual of seeing V equal to IR, but there is another expression, J equal to sigma E. E is the applied electric field, J is your current density, sigma is nothing but your electrical conductivity, right? And then closely related to the concept was that we saw that Vd equal to mu E. Again, this was this arose from that, and in the same context, in the same scheme, what we had observed was this term mobility that I was talking about. This is the low field regime. So essentially, when we had drawn drift velocity versus electric field E, this looks something like this. So in the linear region, Vd is mu E. Mu is the mobility, as I'm saying. And we also saw different scattering mechanisms, like due to the lattice, due to the Coulombic interactions and phonon interactions, and so on, right? And the other transport mechanism is diffusion. That is, if there is a large concentration of electrons, let's say on this side, there's a large concentration of electrons, and very few electron concentration in it, they naturally diffuse from this side to this side, right? So this is, and this the movement of charges, nothing will give rise to a current. That's what I mean there. Okay. So after that, we saw that how drift and diffusion can be balanced in a non-uniformly doped semiconductor, and we arrived at something called the Einstein relation. D by mu equal to kT by q. If you recall, K is a Boltzmann constant, T is a temperature, Q is the electronic charge. And finally, we saw that in a more complex system, that means where we're shining light on a device, there can be generation of electron-hole pairs, and there can be recombination also. For instance, if electron and holes are residing close by, and if you give them sufficient time and sufficient space, they can recombine. And we also saw that so this essentially the total change in carrier density is driven by these four components. Then finally, based on this basic understanding, we moved on to something called the p-n junction. So P is nothing but this is the p-type semiconductor that is doped. This is the n side. We saw that as soon as you form this metallurgical junction, there will be a diffusion of mobile charge carriers, and essentially you will form a depletion region, which is essentially there is no mobile charge carriers here in equilibrium, that is. So there will be positively charged fixed donor ions. On the p side, there will be negative charge fixed acceptor ions. And the different flavors that we saw, like this is an abrupt p-n junction. They can be p-i-n junction. P-i-n is nothing but p, then you have an intrinsic region and an n. P plus n means this p-type is heavily doped. So we saw the charge profile, how it looks like, and we used a depletion approximation. We saw that the electric field peaks at the metallurgical junction. We derived some expressions for depletion width and a very critical parameter, the built-in potential. So to visualize the built-in potential, you can think of something like this. So this is your let me Just a second. So what we had seen is something like this. So this is the left side is your p side, right side is your n side. So this is p, this is n, and this is your depletion region. And the bending, let's say the amount of which bends have bent is nothing your built-in potential. So this is your p side, this is your n side, and at equilibrium there will be a constant Fermi level, something like this. Right, this was in equilibrium. Then we put a forward bias to that, but we saw that this band bending reduced, and now the electrons which are injected from the n side, let's say, can now cross this depletion barrier. They'll drift across this, and finally they'll recombine in the p region. And thus we saw a very interesting chart in which the four components of the current we saw there. This is quasi-Fermi losses arises essentially due to now the equilibrium is broken. So this EFP on the p side and on n side we saw the different two. We injected some carriers, and as I told, the carriers will diffuse. And we also saw the law of junctions, which is np equal to not ni square but np equal to ni square e to the power va by kt by q. Va is nothing but your applied potential. We also saw in high level injection what happened. That means you are injecting so many external charge carriers from a battery that some of the assumptions fail, and thus the potential which we had assumed needs to be the quasi-neutral regions over here outside the depletion region, they also start playing, so voltage starts dropping in that. Usually we don't want to operate in those regions. Then an interesting thing, we saw the reverse bias, that is now your n side is connected to the positive terminal of the battery, p side is connected to the negative terminal of the battery. And we saw the reverse saturation current expression, the junction capacitance. And finally we went into a more deeper analysis in the avalanche in the reverse bias, and we saw two forms of breakdown, the avalanche as well as the Zener breakdown. We saw a couple of applications for them. So a Zener breakdown, for instance, can be used in voltage regulators, and there are very interesting problems that arise from that, the numerical problems. That is a very peculiar p-n junction diode application we saw in the tunnel diode. Tunnel diode is nothing when both the sides are heavily doped, and we saw that its forward characteristics look something like this, if you recall. This is I versus V of a tunnel diode, and we saw that the three regions we had discussed is three regions. And just for the sake of comparison, this is our traditional diode, p-n junction diode, and this one is the tunnel diode. So we saw why it arises here. There's a band-to-band tunneling and the negative capacitance regions because tunneling has started to reduce, and finally the drift carries on like in a traditional p-n junction diode. We had a brief introduction about the LEDs, light emitting diodes, as to how they are functioning. They are essentially in the forward region. So we saw the four regions. Let's say in the IV characteristic curve again, we can just have your four regions. So this is I versus V, and so here let me draw the characteristics. So this is the breakdown, the avalanche breakdown. And so see that in the first quadrant we operate this is the operation for LEDs. In the third quadrant we saw photodetectors, and these are I talked a couple of the applications for them. Essentially, when you increase the intensity, the current increases, right? Because now you're shining light, and the electron hole pairs are generated, and now they'll contribute to the current. In the fourth quadrant is the solar cell. We had not seen it yet, but we'll encounter this in the coming sessions. And finally, we had talked about the Schottky diode. So Schottky diode is nothing your metal semiconductor junction. So one side is metal, another side, let's say N type semiconductor. And now again the same analysis we had obtained. We saw its band diagram was a bit different. So this was the EF on the metal side, and depending on a certain entity is called the work function and so on. So we saw that so this was the Schottky barrier that we had encountered, phi n. And so this is the N type, this is your metal, dotted line is your EF. Then we saw the two flavors, the rectifying and non-rectifying contacts. Essentially your non-rectifying contacts are used to make the ohmic contact with a semiconductor, because a wire coming from the battery has to be connected to the N-type material somehow. That's where these are in use. And finally the mode of conduction mechanism is not your drift which we saw as a traditional p-n junction diode, but rather thermionic. So that is from the previous sessions. Now today I'll be talking mostly about another application of junction, so to speak, in a more traditional sense, which is the bipolar junction transistors. In that, the keyword is transistors. But even before we try to understand what does a transistor mean, how it operates, so on and so forth, I just want to illustrate as the contrast with a resistor. So resistor, as we understand, is when you apply a potential difference. So on your screens, what you're seeing is just assume it to be a pipe, and the blue color you see is, let's say, it's water. So if a pipe is perfectly horizontal, that means the potential on the left side is exactly equal to the potential on the right side. What you're going to see is that the water will not flow in any of the directions, right? So in other words, what you're saying is that the potential difference between the left and right side will determine how much water is flowing. In an electrical sense, will be the potential difference between the two terminals, the left and the right, will determine the current flowing through them. The water is analogous to current here. So as I told, no water will be flowing because it's at the same level. Now let's do a different. Let's modify the system a little bit in the sense that the potential on the left terminal is greater than the potential on the right terminal, right? So this means essentially you're just tilting the pipe towards the right. So right is at the bottom. Now naturally you would expect the water to flow from left to right. Electrical terms, since the potential on the left side is higher than the right side, the current will flow from left to right. A current scenario which is slightly different is now the potential at the right is on the higher side, which you see on the right of your screen. The potential on the left is lower, so naturally the water that is there in this pipe will start flowing from right to left. Or analogously, if you apply a terminal of the battery to let's say a metal, right, and where right terminal is the right side of the metal block is connected to the higher potential, positive terminal of the battery, current will start flowing from right to left. And this is fairly straightforward. This you must know. I just want to emphasize the point that the key takeaway from this slide is that the potential difference between the two terminals, any two terminals, will determine the current flowing between them. No external entity is controlling the current. Transistor is, as you can say, is a combination of two words, trans plus resistor. So essentially trans means from the other side, technically speaking. So what we are saying here is that now some other entity will control the flow of current in electrical sense. And since we are taking the analogy of water, so these are the two terminals that you see, the left and the right, again similar to before, and you can see that they are not the same potential, right? However, now I'll introduce a third terminal. So you can say it's a control knob, right? And I'll try to use this knob to see how much water is flowing between left and right. So let's do that. So what I'm doing, so this the middle terminal, let's say, the left and right are at different potential. You can clearly see that, but the middle terminal is what I can control. So in this configuration, you can see only small amount of water can flow. Okay. So now if I let the system run, so what's going to happen, you can see some amount of water is flowing from left to right, despite there was a huge potential difference between the two. Okay. So what essentially is happening is that this third terminal is controlling the amount of current, or in this case water, flowing between left and right. So now let me do a different thing. Now I'll lower the barrier. So what I've done is that the left and right, their potential difference is still the same. So between the picture in the center and on the left, these two pictures have the potential difference between terminal, let's say A and B, terminal A and B in this case, and A and B is this case, it's the same. So VAB is, let's say, something V0, and here also VAB equal to some entity V0, some fixed quantity. But this time on this terminal C and this terminal C, so this time what I have done is that I have lowered the barrier in C. The water level is still the same, the potential difference between A and B is still the same. However, this time you can notice that more amount of water will flow because I have now lowered the barrier. So essentially I have not changed anything between A and B. The amount of water is still the same, the potential difference between A and B is still the same. It's just that the barrier, the C terminal, I'm playing with that, and now I can see more amount of water is flowing. I can do the reverse also. So again, the terminal A and B are your left and right, and VAB is again equal to some fixed entity V0. The amount of water is still the same. But this time I'm raising the barrier as compared to the central, the reference the reference system, let's say. System on the right, now if I raise the central barrier, C, no amount of water can flow, right? So this is what essentially is happening. What I want to take away is now that a third terminal, which in this case is C, is now controlling the current flowing between two other terminals, which are A and B. And potential difference between A and B remains the same in all the three cases, but you can see the amount of water changes drastically. The electrical analogy is also true, which we are going to study, which we are going to elaborate a bit further upon. This was an important point that I wanted to highlight. Right. In the bipolar junction transistor, the second term is junction. What kind of junctions? We saw, for instance, we had at least talked about two types of junctions till now. The PN junctions, we saw PN junction diodes were a facet of that. And secondly, we had talked about the Schottky junction, the metal semiconductor junction. Here we restrict ourselves to the PN junctions exclusively. Okay. And the third term is the bipolar. So bipolar means, bi means two, polar means poles. So this means essentially what I'm talking about, that the current in such a transistor, in such a device, in such a semiconductor device, is due to electrons as well as holes. So they both can contribute to the current. We saw in the case, for instance, when we had in the last session, we talked about Schottky diodes. There the current transport was due to the electrons itself, not due to holes. So we had seen that. So, but in this case, it's a bipolar device. So, for instance, in some competitive exams or in some university college exams, it might be asked, identify a unipolar device. So that they can give four options: a PN junction diode, Zener diode, bipolar junction transistor, Schottky diode. So and then you have to identify among the given options which are the correct option or options. So just try to remember that when we are trying to analyze a device, it's when you're trying to see it's working, it's a good practice to have at the back of the mind what current is there, but current is due to transport of electrons or holes or both, right? Okay, so as I was saying, bipolar junction transistors is a transistor, means third terminal, which in this case we call base. In the terminology of a BJT, we call this third terminal as base. And the other two terminals which are known as emitter and collector. So base will be controlling the current flowing between the emitter and collector, right? And this is we will see now. I'll see what I mean by that. And as I told, current due to both electron and holes. There are two flavors. So there are NPN BJTs and PNP BJTs. There are more complex forms also, but these are two very basic forms which help us to understand the working of a BJT. So an NPN transistor, in that the electron is the majority charge carrier and hole is the minority charge carrier. So the way we write is that the first terminal is emitter. The first symbol that you see determines the doping of the emitter. Second determines the doping of the base, and third determines the doping of the collector. Similar thing is happening here. This P is for emitter, N for base, and this P is for collector. Okay, and P and P, the holes will be majority charge carriers and the electrons will be minority. Why is it that? We'll see in a couple of slides. So this is just I'm introducing the topic, and this is the schematics, how they look like. So as I was saying, emitter is, as said, N type. It can also be N plus. We'll see in the course of this session why it's N plus. Base is P type, as I told, and collector is again N type. And the three currents that you are seeing over here, obviously this is flowing because you're connecting it to some external circuitry, which till now I've not shown. So just don't get confused by that. Similar thing is happening in base, emitter, base, collector. And what you can see, one important thing that I need you to notice is that the current will be flowing out of the emitter. Okay, and hence the symbol of a NPN looks something like this. So this is very illustrative because the current will be flowing out of the emitter. So we'll draw it something like this. The arrow is pointing outwards from base to emitter. Similarly, in a PNP BJT, the current is flowing in, as you can see, towards the. So essentially, it's because the holes are being injected. Okay, and that's why it's happening. And here electrons are being injected, so the current will be, since electrons are negatively charged, the current direction will be opposite to the flow of electrons, hence the current is flowing out. Here we are injecting the holes, so it's going to happen, the holes injection direction as well as the current will be in the same direction, and hence you see this symbol. So the arrow will be always on the emitter, base is always denoted by this, and the arrow from emitter to base denotes it's a PNP BJT. So sometimes it's not even set, only this diagram you will see and you'll have to identify it yourself whether it's NPN and PNP. This becomes very important when you're solving numericals. From an analysis point or understanding the working, it does not affect that much. You just, because it only talk about one charge carrier to understand the problem, the working of a device. When you're solving the problems and if it has NPN as well as PNP BJTs, you must identify the device properly before solving the problem. Okay, one more thing, as I was telling you, that you see this is N plus, and one other thing you can notice is the area, so to speak. The base you see is quite small as compared to the emitter as well as collector, both for NPN and PNP. This is deliberate. This design is deliberate. So this table just illustrates, just lists what are the things, what are the let's say when a bipolar junction transistor is actually fabricated, what considerations, what two primary considerations we take into account. So first one that we care a lot is the doping. We consider doping is in such a fashion that emitter doping is supposed to be high, okay, base doping is supposed to be low. We'll see why is it, and the collector doping is moderate. So let's say high means, let's say I'm doing 10 to the power 18, and low, let's say I'm doing 10 to the power 15, moderate, let's say 10 to the power 16 or 10 to the power 17, okay, per centimeter cube. There is a doubt by Bhuvnesh. Does arrow mark denote movement of holes alone? No. So so essentially what I'm saying is why this direction is being drawn. It essentially denotes your direction of your current. So that's, so just forget about, okay, let's talk PNP. So in PNP, what I'm going to do, we'll see in a bit that we bias it such a manner, the most common form, the most common way its application is that we connect this emitter base to forward, we make it forward bias. So you can see there are two junctions here. So this first junction is this emitter base, which is a P plus N junction. The second junction is this base collector, which is again a PN and NP junction. So what we do is that we typically connect, I had not drawn this because I did not want to introduce the biasing as of now, but since the doubt has arisen, so what we typically do is that in one of the, so what we do is we connect something like this, okay, forward bias. P is connected to the positive terminal. So what's going to happen, the current will flow in this direction. Just forget about the collector for now, forget about this region, focus only on emitter base junction. So current will flow in this direction, and this is how we denote a PNP. Let's do the same exercise on this. I have to bias emitter base and a forward bias. So this means the emitter, which is the N terminal, will be connected to the negative terminal of the battery, and this is a forward bias now. So how will the current flow? Current will flow something like this, right? So the current will be coming out of the emitter and entering into the negative terminal of the battery. How do we denote it? Similarly, if I try to denote it like this over here, something like this. So current will be coming out of here. This is the way just to denote. This is just a symbol to, this is not the direction of electrons and holes. This is to illustrate the direction of current, and more importantly to distinguish between these two devices, because when you go to the market and you buy them, physically they look similar because they're in the same external plastic casing. You will not be able to identify, right? There are some markings on the device itself, but when you draw on the paper, so how will you distinguish between NPN and a PNP BJT? This is how we distinguish by just this arrow. This arrow primarily denotes the direction of current when we apply a forward bias. That's all that direction of that arrow means, okay? Not the flow of electrons or flow of holes, the flow of current in both NPN BJT and PNP BJT. So if its arrow is marked like this, that means current will be flowing in this direction. Similarly, in a PNP BJT, current will be flowing in this direction, provided emitter base is forward bias. So that's the assumption that we are making. All right. Have we got Bhuvnesh? Okay. Yeah. So where was I? Yeah, I was talking about the doping, that why we do it. I'll come to it in a couple of slides later, but that's how we do it. I'll again revisit it, but since this is a snapshot of the complete picture of a BJT, I just felt important to introduce it here itself. The second thing, the second difference, the second term that we in this table I have listed is width. So this width, you can see that the base is very narrow over here. So emitter is moderate, so which we typically form in a PN junction. It is like that. Base, we deliberately keep it narrow. Okay, why we keep it narrow, I'll come to that, but essentially it's just so that the electrons which are coming from the emitter, so this is, you can see it's a NP junction, right? Electrons will be coming from the N side if it's forward biased, and what we typically see is that it'll recombine when they reach the P side, right? And that's, we again, I'll just in the fourth session, if you recall that I had talked about that there are different components of current in a PN junction diode when it's forward biased. So just revisit that if you do not recall. Just try to recall. Just revisit that if you're not feeling comfortable here. Okay, and then why this is narrow? Because we don't want them to recombine. We want the electrons which are injected from the emitter, we want to travel across the base. So if the base is very wide, the electrons that are coming from the emitter side, they'll recombine here. This will not be a BJT, then this will just be simply a PN junction, forward bias PN junction. We do not want that. Base will not be controlling anything now. Emitter and base will be controlling together. We don't want that. That's why we want it narrows, to reduce the chances of recombination, and that is also the reason we want the doping to be low. If we have low doping, then there are more centers, then there are less acceptors available for the electrons coming from the emitter side to recombine. I'll do this in a more detailed way when with a different diagram. The collector is wide because a large amount of current will be flowing into that, and we want to dissipate the heat. So this is essentially not so much from an electrical perspective, but rather from a thermal perspective. So we want the area to be wide enough so that the heat generated is reduced. So that's the reason for that. Okay, so this now I believe I'll take a pause here. If you have any doubts, comments, suggestions, please feel free to speak, because now I'll be building up on this this basic understanding of a bipolar junction transistor, and from this point onwards I'll be focusing only on NP and BJTs. So as I told, PNP BJTs, I have just given an example, thanks to Bhuvnesh for asking that. The way it's different is nothing but all the analysis when I talk about in NP and BJT, just replace electron by hole and hole by electron, and you'll get the same working essentially. Okay, right. So let's move forward now, so this is a question, because this is just on the basic understanding that we had talked about till now. So when transistors are used in digital circuits, they usually operate in, so the reason why I put this question before I introduce biasing is just to illustrate the fact that in digital circuits, essentially what you just simply understand is this on or off. We want any device to either be on or off, just the two states. So just imagine it like this. So let's say we have let's say output with respect to time. Okay, 0 is on, let's say, 0 is off, so let's say it's off for some time, and then it turns on, it remains on for some time and turns off again, off for a long time, now again on for some time. This is the same level. The levels are not different because we're talking only two levels, high or low. Okay, there are no there is no other secondary level. So this is low, means it's off, it goes there, it becomes on, it becomes off again, let's say after some time, remains off, becomes on again, remains on for some time, becomes off, and then becomes on again, and let's say it remains on. So this is the on state I'm talking about, and this is the off state. I'm written output here, but essentially what we are measuring in electrical circuits are voltages and currents. Okay, so this will have a certain voltage, let's say V0. Let's say this voltage, let's say we call this V on, let's say we call this V off. I've set it to be 0, right? But a certain voltage level will correspond to off state of 0. Okay, it's not that it's usually it can be 0, but not necessarily. Okay, for instance, there are some courses on NPTEL, maybe you'll encounter in your bachelor's, or you have encountered in your master's and so on, some digital circuits, some like flip-flops we have, latches we have. There we do not talk about the explicit voltage levels, like voltage is 1 volts, voltage is 1.5 volts. No, we only talk about on or off. That's it, nothing else. Okay, so how do we again, when we make those devices in digital circuits, we make those flip-flops, we make those latches, timers and whatnot, the underlying thing in them, I'm giving some examples of digital circuits. Let's say I'm talking about of an SR flip-flop. What it is, you need not go into that. It's just a device which is used to perform some digital function. Okay, what it uses is something, you must have heard of these gates, the different gates like AND gate, OR gate, NOT gate, so on, right? Those gates are in turn made of a device. Usually what we use is a MOSFET. You can also use a BJT. This T in both the cases stands for transistor. So as I told you, BJT is one family of transistors, right? There's another family, FETs we call them, okay? Field effect transistors. They have a slightly different mechanism. I think we'll come to that in a couple of weeks from now, I believe. And that's week 8. MOSFET is week 8 if I recall. This is week 6 we are talking about. So there are two flavors of transistors, BJT and FETs. These are the building blocks essentially of these logic gates. Logic gates which are essentially used in your flip-flops, and which the complexity just keeps on growing. Okay, so what I was there is that since these are the building blocks of them, and this is known as switching, this operation is known as switching. On to off, off to on, and so on and so forth. Okay, now to understand how does we'll restrict ourselves to BJT, how can we use a BJT to perform this switching function? Okay, so this is your, as I told you, I'll be considering only the NPN transistor BJT. So you have this NPN, again N plus denotes heavily doped and so on, and you see the currents direction. So as there are 3 terminals, right, you can bias them in 4 different ways. So there are 2 ways of biasing this terminal, base emitter junction, and there are similarly 2 ways of biasing the base collector junction. This is the base collector biasing, this is the base emitter biasing, and there can only be 4 combinations, 2 into 2. So this is the complete list, in fact. So what we have is that the most common so what in the previous slide what I had talked about was this active region. This means base emitter is forward biased, so you connect this to emitter to the negative terminal of the battery, base to the positive terminal. Similarly, this is the other junction, PN junction. If you connect it reverse bias, this is known as, the operation region is known as active or forward active. Active or forward active. Okay, if you have however both of them in the forward bias, so this junction, PN junction, as well as this PN junction in the forward bias mode, both of them, you'll enter region which is termed as saturation. Okay, essentially what in this case what happens is that your base loses a lot of control. So the transistor is traditionally not working as in the traditional sense of the function definition of the transistor. Okay, this is forward and this reverse. Essentially in this case, in the case 3, so what you have done, base collector is forward bias and base emitter is reverse bias. This is exactly inverted of the first case. So first and third are, you can see we have changed the roles. and hence this is called the reverse active. But please note, we have not changed the doping. Collector is still moderate doping and emitter is high doping, so that roles have not changed, and thus this is the reverse active mode. Very rarely you see applications in this. So I doubt you will encounter any numericals or otherwise related to the role of a BJT in the reverse active mode. Reverse is fairly used when we don't want to conduct any current. So this means if both the terminals are reverse biased, naturally you can see that only the reverse saturation will be flowing on the both sides. And typically, if you recall the problems that we had solved in the last session of the PN junction diodes, where we had seen the reverse saturation current, that is usually in picoamps, right? And then the currents which you typically see in the forward bias currents are usually in milliamps. So essentially, in the reverse case, we say the device is in cutoff. In a more common term, we can say the device is off. Technical term is cutoff. We'll such the device is off. This means no amount of current is flowing. And this state, this cutoff state that I'm talking about, is used as in the state of a digital off. I talked about the digital on and off in the last slide. When we are in the cutoff mode, we are essentially means digital is off. This digital state is off, and this saturation state, when we talk about, we say it's on. You can see that both the PN junctions are conducting, so we'll say that device is conducting to maximum capacity, so to speak. The base is very it's not behaving like a controlling feature, but so what we say is that when it's forward bias, base collector as well as base emitter, we say the device is in the saturation region, is operating saturation region, and digitally we mean it's on. This diagram illustrates all these four regions. Okay, let's first start with cutoff. Cutoff, as I told, very less amount of current, negligible current is flowing, and this is what is known as the output characteristics. Output characteristics means I'm denoting IC, the collector current, because that's where we usually take the output from, versus the VCE. So essentially, what you can think of it is something like this: that there are different. Okay, I'll draw this. So this is, let's say I'm connecting, I'm denoting it forward bias, but this bias can change. Okay, so this is VBE, let's say, and this is VBC. So this VBE and VBC is the biasing that I've written here, so they will change. So when both of them are reverse bias, both these junctions, you are operating in this, you can see very less amount of current is flowing, no matter how high VCE you choose. Current is not even flowing, right? Reverse active is not shown in this diagram. It will be essentially somewhere a positive forward active. This means in the third quadrant, which are not showing that. So this is the off region in the orange that you see. In the on is the forward. This is the saturation region, let's say below 0.7 volts. In this region, this is the saturation region over here, this region. This is when the device is on, so you can see the current is 0 here, but the device is on over here. And what you can also see is that IC versus VC is a linear relation, right? So it has a resistance associated with that, right? That's why we say it's behaving like a switch now. So what we do is that when we are operating in this saturation region, we can say the BJT is something like this. And this switch is closed if we operate in forward. So now you see only a resistance, which you are seeing over here. This value of resistance depends obviously on IB, for instance. It's not that the base is not playing any role, it's still playing some role. But this state is known as on. The third state that you see is forward active. It's this region, which is almost flat, not exactly, almost. We'll see that why does it have a bit of the slope, even in this case. Where was it? Yeah. So this region is called the active region, denoted over here. So these are the four regions, and if you increase the collector voltage to a huge amount, then the device will break down, which we have seen. Avalanche breakdown is not that it's non-existing, it still exists. If you increase the collector bias, let's say, to a ridiculous amount, the device will break down, because essentially these are still PN junctions. The avalanche breakdown will still exist. Okay, Zener will not rise, because if you recall, Zener is we had seen it arises in case of when we have heavily doped P and heavily doped N plus P plus junction. There's no N plus P plus here. Only emitter is heavily doped. Base and collector are base. Base is in fact P minus rather, and collector is moderately doped. So these are the three regions, four regions rather, that we encounter. Reverse active, as I told you, is not shown. It will be in the third quadrant, but that's of very least relevance, because the device operation is not efficient in that case due to the doping factor. Okay, sometimes what also happens, again you will encounter this when you use this BJT in some problems, let's say where we have resistors, and we want to determine the current flowing between them and so on. So we also draw a load line. So load line is essentially when you connect this this fellow to an external load, RL, right? So RL will also have its role, because it's connected to some external battery. The maximum voltage that it can supply is VCC, and the maximum current can have is VCC over RL. So based on what the IB is and where this load line is intersecting, that determines something called the quiescent point. We don't have problems on this, for instance, this assignment, I think, but that's a good point as to what is a quiescent point. Quiescent point is nothing but the intersection of a load line with the output characteristic. So for instance, if we are operating at IB2, this will be our quiescent point. And let's say if you are operating, if you are providing the current as IB1, this will be a quiescent point. So quiescent point can change. Usually RL we don't change, VCC we don't change. It's just that we change the knob. That's why I'm saying it's a transistor. Using just the third knob, the IB that you have, you can change where you are, what kind of current or what kind of voltage can be dropped across the load. That's a transistor means. A resistor cannot do that. If you connect, for instance, in case of a transistor, if you connect, if you draw this circuit, let's say, you have VCC, you have RL, and you have some another resistor, let's say R1. The current will be fixed. The current in RL cannot change, however, unless you change VCC. But however, here if you change IB, right, you can change how much current is flowing through this transistor, whether it will be IC1, this corresponds to, so this current will be IC2, this current will be IC1, I'm saying here IC2, IC1, and so on. Just by changing the base current, you can alter the current flowing through this load resistor, which is shown over here. Okay. So as I told, in the digital regime, we are only interested in on and off, on and off, on, off, on. Let's say keeps on. So this is, let's say, output, or digital output rather. This is time. So this is on and off state, I told, is something known as the cutoff. So this cutoff region corresponds to the off state in the digital world, and the saturation region, right? Saturation region, that it turns out as on. Saturation, please remember, when the base emitter as well as base collector both are in forward bias. So that's an important thing to remember. And just give me a minute, I'll be back. Just hold on a second. Okay, thanks for waiting. So the next, one second. Yeah. So this question is essentially builds on the the discussion that we have already had. Remember, depending on the biasing of the two PN junctions in an NPN transistor, in an NPN BJT, we classify different modes, right? So let's just see what this question talks about. Here we are given two BJTs A and B, and they're operating under the following conditions. So BJT A has the emitter base junction is forward bias and collector base is reverse bias. On the other hand, the BJT B has emitter base is forward bias and collector base is forward bias, and we had to identify the correct statements, and this option has more than may have more than one correct option. As I have been saying, attempt these questions only when you are confident of arriving at all the correct answers. They usually do not have negative marking, but still, if you invest 5 or 10 minutes and you do not mark all the correct answers, you'll not get any marks. You'll not get negative, but you'll also not get any. So just a caution regarding that. Okay, so let's analyze, and I again bring this table that we had seen in the last slide or so. So for BJT A, emitter base is forward bias. So emitter base is this, it's forward bias. So first two rows, and collector base is reverse bias. So collector base is reverse. So this means this corresponds to BJT A. Okay, then we have a second transistor BJT B. In that we have emitter base is reverse. So emitter base is reverse. So either of these third or fourth row, and collector base is forward. So collector base is forward. This means this is BJT B. Okay, so what we have seen is that BJT A is in forward active. I've been saying active or forward active is the same thing here. So A is in forward active, yes. B is in reverse active, yes. So these two options are correct, but let's see which one among them. Now in the previous question we had talked about the application of a BJT. I told you they're used in logic gates and so on, the building blocks of the sequential circuits or the digital circuit, so to speak. And in that sense I was saying we require them to be on and off. So we had if you recall, for that application we wanted them to saturation and active region, right? But yes, you're correct, Bhuvnesh. So in this problem we need to identify which of these transistors can be used for amplification purposes, and the key point here is efficiently. Okay, so first we need to see whether they can be used for amplification purposes or not. So for amplification purposes, a device has to be biased in the active region, because see, if it's in breakdown, it will just be used only for once, and it will have no lifetime. Essentially one operation and the device is burnt. It's of no use for us. We don't want that. For testing purposes, yes, we do that sometimes. We try to see what is the breakdown voltage of that device, and then only we can determine this VCE max, because you must not apply VCE max at a given point of time. Not only one device is not manufactured, thousands and millions of devices are manufactured. In each batch some devices are taken up for testing, right, which determine the breakdown region or the cutoff. You see this VCE max, how much we can apply, right? So in a batch, let's say, so we test that, but the majority of the devices still go out to the market in your phones and whatnot. We should not apply more than this bias. Okay, so this region is useless, and I have been talking about in the amplification you want some current to be flowing, so you definitely don't want to be in the cutoff region. Saturation region, I told, saturation region is used for switching purpose, right, on off. So saturation denotes essentially your on case. But what we have here is that in this, the active region, in this you can see that the IC, the collector current, let me just say that this is the IC, let's say IC6 corresponding to the base current IB6 between the points marked as B and C. Between these 2 points, if you bias this device in such a manner that VCE between 0.7 and between less than the breakdown voltage, you bias it somewhere over here. The question point as I've been talking about, right? It's a different case. Now what you do, so now you have fixed the DC point. You have now fixed the DC point. Now what you do, you just apply very small AC voltages to that. We do not have time for instance, to go into the small signal model of a BJT, right? But what I'll do is that I already have some videos on my channel regarding these devices. So what I'll do is that when I upload the session for today, I'll I'll just add them in the description or in the end, so that if you are interested in seeing the small signal model and so on, you can just go through that. For now, I've just I've just pasted the link of the YouTube channel in the chat box. But I'll put them in the description. So if you're interested in that, how does a small signal model of a beat. So when we're saying it used for amplification, but how does it actually do that? So the mathematics and the analysis of that, and some applications and some numericals, you can see that in those videos if you are interested. But for now, as I've been saying, you need to be in the forward active region to serve the application of amplification, right? But as we can see that BJT-A is biased in forward active, so yes, so it can be used. BJT-B is in reverse active, so it cannot be used for amplification purposes, okay, efficiently. As I've been saying that, see, because in NPN, let's say this is NPN, this is N plus P and N, right? You can see that base will remain the same. If I switch the roles of emitter and collector, how it's going to change? The doping is the thing that is different, okay. And also I told you the area is different. The collector has a wider area for heat dissipation. So there are some even if I switch the active and reverse active, if I essentially reverse the roles of emitter and collector, it still is technically an NPN BJT. The problem is that the efficiency reduces, okay. And what those efficiencies are, how they come about, for that I'll have to go into the working, the actual working of an NPN BJT, which I had promised like 20 minutes or so back, that how is it actually working. So I'll go into that. But till now I've been talked about biasing in sufficient detail, I believe. So if you have any doubts or comments, you may ask. Because now I'll be going into the working of an NPN BJT, just a quick summary, not a 1 hour lecture on that. For that, you have the videos from Professor Digvijay. Feel free to visit that. But just a quick snapshot, so that the basic things when you're solving a problem, the idea is that even when you're approaching a problem, you should have these things at the back of your mind. Oh, BJT works like that in forward active. Okay, if I change the bias of let's say collector bias junction, such and such thing will happen. So in the back of your mind, it's a good habit to have an idea as where the electrons are, it's the flow changing, and so on and so forth. Okay, so now let's see the working of an NPN BJT. As always, PNP is still there. I'm not going into that. The analysis just differs a bit, that's all. Electrons in place of electrons, it's the holes we'll talk about there. Okay, so let's see that. So on your screens now, first of all, I need to identify what this device is. So anything, so I have told you it's an NPN. You can also see emitter-base collector written. But even if it were not written, let's try to identify this device, what this device is, purely based on its band diagram. So this is a band diagram. This is electronic energies on the y-axis, and your your position on the x-axis, right? So we still have that. We still have that. And now let's just try to identify what kind of a device it is. Okay, first we see that the EF is horizontal. So we can see there are 3 distinct regions. So we have an N-type semiconductor, P-type semiconductor, and again an N-type semiconductor. Fine. First thing with the EF is flat. So this means this diagram that I have is at equilibrium. This is a device which is at equilibrium. Fair enough. You always start the analysis when you are at equilibrium, then you apply the biases. Okay. Second thing I notice is that here EF in this N-type region, EF is closer to EC, right? Very close to EC. This means it's heavily doped. Okay. Second thing I note in this P-type region, and first let's come to the collector. You see EC is rather far away from EF. This means if I compare emitter and collector, emitter is heavily doped as compared to the collector. Okay, base is P-type doped. It's illustrative. Base should actually is very low doped. let's just go ahead with that. So we can see that EF is closer to EC in the collector. That means it's an N-type material. Similarly, in this green region that is highlighted, you see Fermi level is close to EV, the valence bias, as compared to EC. This means it is a P-type material. So even if I have not written this N-type, P-type, N-type, you must be able to identify this material is N-type or P-type just by where the Fermi level lies, relative to their respective conduction valence bands. Okay, that's a very important exercise that becomes very handy, for instance, in competitive exams. Just by looking at the band diagram, you can identify first whether it's at equilibrium or not. Second, it's an N-type material, P-type material. What is the nature of its, what's the extent of its doping, high dope, moderate dope, low dope, and so on. And then you can go in the analysis. It becomes very easy to analyze that device now. Okay. Okay, so let's go ahead and analyze this device that we have on our hand. And as you know, so let's just focus only on emitter base, only on the left side, this region. You'll obviously form a depletion region, right? And since this is N plus P rather, so I'll write it as such. This is N plus P type. So most of the depletion region will be on the P type. You know that because this is heavily doped, and we had seen those expressions due to the charge neutrality, like Na times xp equal to nd times xn, the charge neutrality. Refer to your I think, I don't know, it's second or third, I think it's a p-n junction session, fourth session I believe. Yeah, so depletion is generally primarily on the base in this emitter base junction. For the base collector junction, we do not have much information, but just by looking at this, it looks like it's going to be asymmetric because the Fermi levels are not equidistant from conduction valence band, but it will not be as severe as we have in case of the emitter base junction. This is at equilibrium now. Now what I'm going to do is, now I'm going to apply some bias. What bias? As we had seen the table, if you remember, the emitter base and collector base, there can be 4 flavors, right? What I'm going to do, emitter bias I'm going to do is forward, collector base as reverse. That means I am operating in forward active region of that output characteristic that I have shown you a couple of times, the IC versus VC plot. Just try to remember that. Okay, so now let's see what is happening. So this is just a macro picture. So you can see, as I told you, in this region what we typically see is emitter current is coming out, hence the direction. If you recall that, the symbol of it looks something like this: collector, base, there is an arrow here, and this is emitter, right? So you can see again the current is coming out of the emitter, and what we see is that in this N plus P region, this has to be forward bias. So let's see, N should be connected to negative terminal, it is connected to the negative terminal, P is connected to the positive terminal, and collector base has to be reverse bias. Collector base has to be reverse bias, and you see this. So reverse bias means N terminal should be connected to the positive terminal, just connected to the positive terminal, and this P is connected to the negative terminal. Okay, so this now I've completed the biasing. What's happening over here, the flow that I've shown here, that will analyze in this picture. So again, I'll just focus on this, and let's try to identify first of all the class, whether it's at equilibrium or not. It is not. You can see the EF shown in dotted line as 3 different quasi-Fermi levels. So I'll call this EF, let's say emitter, right? I'll call this EF base, and this is EF collector. Just like EFP and EFN, right, in p-n junctions, similarly you have 3 Fermi levels. So now you can clearly see is that there is a bias being applied. There is an external stimulus that have been applied, and that's why the Fermi levels are not the same. Okay, what is the nature of Fermi levels that I have applied? Now you can see that, just compare the base emitter base junction, right? And again you can see EF is closer to conduction band, so that is N type. So I'll not explain that again. We had already talked about this. Now let's compare the emitter base junction between the top and the bottom figure. So what you can see is that the extent of bend bending you can see is reduced significantly. So what this means is that it's a forward bias. Okay, only in forward bias the band bending reduces. It's VBI minus VE. VBI is essentially what's happening over here. This is, let's say, VBI. Here it's not that, it's VBI minus VBE, the applied potential. VBE is the potential that we have applied. And once we had done that, now the diffusion, now what's going to happen is, now the electrons which are there, I'm injecting some electrons on the emitter, remember, connected to the negative side. So I'm injecting a lot of electrons here. What they'll do is that they'll diffuse across this region, right? Not diffuse, rather they'll drift across, because an electric field that exists over here. This distribution is just devoid of any mobile charge carriers, again remember that. Okay, when they come to this side, on the base side, no, now the base is p-type dope. There are a lot of acceptors that are available here. That's why, that's one of the reasons that we want the doping to be as low as possible in base. We want the doping to be low. Okay, so the electrons that are coming from the emitter, which have now drifted and come to the base, they should not recombine. Very few of them recombine, and hence you want two things. First, what are the two things? First, the amount of background doping that is of holes should be low. First thing. Second thing you want is to be this is to be very small. The width of, sorry, this region is to be small. So so one more thing, this region, this width is written as WBN, and WBN means neutral base width. Please understand that the metallurgical junction will be somewhere over here. And let's say this has over here. So this is your metallurgical base width, WB. That's not of interest to us because there's a lot of depletion regions on both sides. What we are interested in is what's happening in this region, because the recombination can only happen here. We want WBN to be as low as possible, and yeah, if WBE is lower, the chance that WBN is also lower. So that is the case. So we want deliberately, when we are fabricating such devices, especially for amplification purpose, remember, amplification purpose, we want to be in the forward active mode. Recall the output characteristics. Okay, so yeah, so that's that, and so that's why we want the doping in the base to be low, and the base width, in fact the neutral base width, to be as small as possible. Now let's say very few amount of electrons recombined in the base, and the majority reach this edge. Now what's happening, this base collector is reverse bias, VCB, and is connected to the positive terminal. There is a huge amount of electric field, and you can see this is reverse biased. Why? Because compare with the equilibrium state, so it had some band bending, let's say VBI2. Now you can see this band bending has increased. Let's say this is VBI2 plus VCB. This has increased. Visually you can just try to see that. So this has increased. Now there's a strong electric field. So the electrons which we hope majority of them, heavy majority of them, which were injected from the emitter, diffused to the base side, and they have not recombined in the base, and now they have traveled to this edge of the depletion region of the base collector. Now there's an electric field that exists, and they'll simply be swept away and collected on the other side. So you can see there's a positive terminal of the battery which is over here, and the electrons can now just keep on flowing in this direction, and the current direction is naturally reverse. That's why you see in the pink region denotes the flow of the electrons. So we injected a large amount of electrons, right, over here. You see they're diffusing. They diffuse here. A small amount of them have recombined, which we have denoting as the IB, right, the recombination current, which we are seeing over here. There are two other components which I'll come to, but I'm just please note that in this discussion I've completely ignored the holes. I'll bring the holes, but just for now let's focus only on the electrons. And now a majority, we hope a heavy majority of them have drifted across and now reach the collector, and now you can the electrons can now flow out to the positive terminal of this battery, and thus the current direction will look something like this. So that's that. And one more thing, see, this is a circuit, essentially electrical circuit. It will follow the Kirchhoff's current law. Okay, so in this black box, the current flowing out should be equal to the current flowing in. Current flowing out, so this is coming from Kirchhoff's current law. So this is current flowing out. See, IE is flowing out, and these are current flowing in, right? IB and IC are the current flowing in. IC is here. So this must be satisfied irrespective of whatever is happening inside. If you take a macroscopic view, a bird's eye view, this is how it will look, that there's some current flowing, IE is coming out, and IB and IC are flowing in. How they're flowing in, which I'll try to explain it over here. Okay, I'll again bring this picture. This is from the last slide itself. This is we are in the forward active mode again. Now what I'm going to do, I told you I'd ignored the holes in the previous discussion. Let's not ignore them anymore. So you can see the holes which are over here. Let's try to talk about them. So if the electrons are diffusing over this barrier, it's a forward bias now, the holes will also diffuse because it's a PN junction, right? So it's not that the holes will not diffuse. So let's call this electron that are diffusing, the current due to them, IEN. This is the same nomenclature that is followed in the video lectures. And let's call this current which is flowing from base to emitter as IEP. Okay, IEP is due to the holes that are flowing. Now that this current will, you can naturally see, the holes will keep on flowing in this direction, they'll correct it on the emitter, right? So IEP, that's why this IE is being written over here. Okay, so yeah, so that is that IEP. Now let's try to write some expressions for IEN and IEP. It will be QDN over ln that, if I recall, it will be Ni square over N doping of base, so Na in base, and I think ln is that I might be misplacing this column because the term of interest is on this. Go ahead.
You are correct, sir. It will be Na only.
Sorry? Can you repeat?
It will be Na only, sir.
Okay, yeah. So, and this
will
QVBE over KT minus 1. And similarly, the emitter current due to holes will be something dP over LP Ni square. This Ni is the intrinsic concentration, and this will be the of emitter, so doping on the emitter side, and this term will remain the same. So D and DP, LN, LP, they do play a role. I'm not saying that they do not play a role, but the control that we have is essentially of doping and the bias, but this bias term is the same in both the cases. What we have under our control is the doping. So what we have is the two terms that we have under our control. First is this one, and second is this one, right? So let's say if I make doping in emitter, the D stands for donor, much larger than the acceptor doping in the base, what will happen is then this will cause IEP IEP to be much less than IEN. Okay, and please remember that total emitter current is contribution of both IEN plus IEP. Okay, so then if this is the case, then IE will be approximately equal to IE, which is what I want. This is an NBJT. So you see, that's why in this picture, if I make the doping, if I dope during the fabrication of this device in such a manner that I am able to have the respective dopings in such a manner that the primary current is due to the contribution of electrons and very minimal is coming through holes. Okay, We do not want that. And as I've already told, that if you have low doping, that also benefits in that there'll be lower recombination in the base. So the base current essentially comes through two components. First is the recombination current that you're seeing in here. Second sometimes is also added with the IEP, the whole current that is flowing. Okay, so just keep that in account. And in all this analysis, what we had ignored is, I should bring it up now. In the complete analysis, see, this is a reverse bias junction base collector, right? If you recall, base collector, if a PN junction is reverse biased, right, there is a JS, the reverse saturation current, that is flowing. We are ignoring that in this analysis, and that makes sense because the amount of electrons that are flowing here, they usually contribute to some milliamps of current, right? And some electrons, let's say, which are flowing in this direction, right, they also contribute to the current. It's not that, sorry, the electrons will be flowing in this direction. Sorry, the current had mistakenly to the direction of the current, which are flowing in this direction now, right? This is your JS, reverse saturation current. This is usually in picoamps. That's why in this complete analysis we have ignored this term. The reverse saturation current is still there, but since the orders is 10 to the power, in this case 9, or let's say even 6, 10 to the power 6, it will not play any significant role. What does play a significant role is, I'll come to that. I'll come to that in a later point of time. If you recall, VCE versus ICE had a slope to that, right? But so where is that coming from? If we change the VC, how is that changing? We know that the emitter current has a exponential dependence on VBE, which we expect. But why is changing VCE changing this current, the collector current? Right. So we'll come to that. But till now, I have tried to explain the working of an NPN BJT. First, we just looked at the picture just from the biasing. Second, then we peeked into the NPN BJT when it's working forward active mode, and I considered only the electrons. Then in this slide, I also brought the holes, and that illustrates that why the dopings have to be that we have to dope our material in such a fashion, dope our device respective region in such a fashion that we encounter a higher amount of the current coming from, higher percentage of the current rather coming from the electron flow rather than the hole flow. All right, just a second. Yeah, okay, so that's that. Now let's try to solve some problems based on the understanding that we have till now. Okay, and there are a couple of terms that have been written here. I'll try it. I did not bring them in the last slide. I just wanted to tell them through a numerical itself. Okay, so let's just see this problem. Excuse me. So the question says that for an ideal PNP transistor, so no more NPN, we have to now live with PNP. The current components are given by IEP, IEN, and ICP. I'll draw this diagram again. So what's happening? This is a PNP transistor. So let's first change this. This is P, this is N, and this is P again. And the current directions will also be naturally change. Okay, and so this VBE, so since this has to be forward bias, so this will be something like this, and again they will come, so this has to be negative bias, so it will be something like this. Okay, this has to be reverse bias, so P terminal has to be connected to the negative terminal of the battery. So rest all of the picture remains the same. And yeah, sorry about this diagram. I did not intend to bring this here, but let me just still say. So just assume. Okay. I'll try to explain it just using the analogy here then. So this was, so please remember that IE, First term that we are seeing here is the emitter efficiency. So let me just first write the terms. So we know that total emitter current will be equal to the emitter current due to holes plus emitter current due to electrons. Okay, so let me just find what that is. So that is 6 milliamps plus 0.01 milliamps, 6.01 milliamps. That is the total emitter current. And the total collector current, ICP, remember it's written ICP here, so this is the same current that I'm getting from here. Okay, this is ICP. Why ICP? Because just please recall that I'm ignoring the reverse saturation current, so the electrons will not have any component. So ICP, these are the holes that are coming from this side, and I'm collecting them over here. This is just a picture from an electron perspective. The holes, in this case we are talking about P and P, so the holes will be connected to the connector. So ICP now will be, has been given as 3 milliamps. Okay, right. So the first term that we have over here is emitter efficiency. Which is also given by this symbol gamma E. So it is, in case of an PNP transistor, it will be IEP over IEP plus IEN. This is for a PNP. That is, the majority charge carriers are holes, that's why we put them in the numerator, and the minority are electron. We put them, the total emitter current essentially is put in the denominator. Since we are interested in whole current, that's why it's in the numerator. This is for a PNP. For an NPN, it will be IEN over IEP plus IEN. So IEP is given as 6 milliamps, and the total current, the total emitter current is 6.01 milliamps. So you can clearly see, even in this, 6 milliamps compared to 0.01 milliamps. So it's at least 2 orders smaller, right? So let me get my calculator. Just a minute. Okay, so 6, this should be very close to 100% rather. Still I'm going to 0.998. So this number is 0.998. What's happening is that this emitter is efficient to the extent of, yeah, thanks Bhuvnesh. This emitter is extend to 2 parts per thousand, let's say. Okay, so a heavy majority of the current is being contributed by the holes, which we want in a PNP transistor. The second term that we have, I'm going to do it in green, which we need to find is the base transport factor, also given by the symbol B. As the name suggests, the base transport factor, which means is that how many majority charge carriers have been transported to the base collector junction. Okay, in this case we are interested in holes, so that means how many holes have reached the base collector junction. So how many holes have reached this point? That's what we want. How many holes have reached there? How do we know? Which are given by ICP, because those are the number of holes that are collected in the collector, right, which come out as the current. So ICP is the total number of this is holes, not electrons in this case. Okay, so ICP is the total number of holes that have reached here, and all of them we are assuming are coming at the collector, divided by IEN. These are the number of electrons that have reached at this junction. So the rest is essentially what I've recombined. Okay, so let's see that. So we have ICP as 3 milliamps, and IEN, the electrons that have been injected, that have diffused to the base, they are IEN is what, sorry, IEP. This is a PNP transistor, so we must need IEP. IEP was 6 milliamps. So this is 0.5, 50%, and this is really bad. This means that if you are injecting, if the holes that have reached at this junction, let's say are 100, only 50 are reaching there, the rest 50 are recombining in the base itself with the electrons. This is a PNP transistor, please remember that. So this is not a good transistor. This is not a good transistor at all. Why it's happening, whether we have the solution to that would be you just increase your base doping, or there might be the base width, neutral base width might be too large. We don't know what are the geometrical and the geometrical parameters or the doping parameters for this PNP device, but we can clearly see is that much is very clear, that this is not a good device for amplification purpose, that is. Okay, because a huge amount of holes which are being which reach across the depletion region of emitter to the base, they're not going to the collector. In fact, 50%, only 50% are able to travel across. Write this. Only 50% holes. Just a minute. Are able to cross neutral base width. Okay, so how do we improve? So there are two ways. Reduce NDB, the dopants, the donors, because this is an NPN transistor, and or reduce WB, base width. So though if you try, let's say, these two things, maybe this horrible 50% holes which are not able to cross, maybe more of them will cross. Okay, so that's the brain part comes in. The rest of it is very mechanical. These expressions you have in your lectures, video lectures as well. So this was the point that I was trying to put across. Let's just complete the problem. So the answer is 0.998 and 0.5. I'll go with this option. This is the closest one that we have. Okay, technically it's none of the above, because if I round it off, I should round it off to 1. So such kind of problems do arise for when I was writing. I think when I was writing one of the competitive exams, I had run this rounding off error. So when you come across this, just trust your instincts and just make sure you have rounded off correctly. And for instance, I would have marked none of the above, but I know the solution to this problem is given as B. That's why I marked it as P. But if this were in a competitive exam, I would have marked it as none of the above. The reason is because if you round it off 0.998, it should be 1. Simple as that. And once, usually you can also challenge these answers, especially in competitive exams. Not so much in your college or university exams, but in competitive exams you can challenge it. So for instance, if you find that the answer key has this as the option, correct option, you can say that no. Send them the solution and tell them I have obtained as 0.98 and D should be the correct answer, because when you round off 0.998, it should be 1, not 0.99. And you can win that because it's a very straightforward claim. Okay. So yeah, in this we had talked about two terms rather, based on the understanding of our in this case rather PNP transistor. We talked about the emitter efficiency and the base transport factor. These terms we had seen in a more qualitative way in our last discussion, but now I have put some numbers and some names to them. So that's all. Okay, so sorry. So next question that we have is calculate the approximate value of beta of a transistor with emitter injection efficiency of 0.99. So what we have been given is 0.99. Base transport factor given by B is 0.96. So you see it's 96%. Only 4% of if I assume it to be, let's say, an NPN transistor, only 4% of the electrons are being combined in the base. That's not so horrible. We can live with that. Okay, so there's another component called alpha, right? Alpha is given by ICN. If I recall, it is IE. Yeah, so I can write it as ICN over IEN times IEN over IE. You see the IEN cancels out. This is again, this analysis is for NPN. For PNP, just replace N by P, and that's all. The first term that you see, ICN over IEN, we have seen this nothing but beta, the base, B, the base transport factor, and this first term that we see is nothing but the emitter injection efficiency. So we see the alpha value comes out to be 0.99, 0.96. We find out what it is. 0.99 times 0.96. This is 0.95 approximately. So this number is 0.95. Fine. There is another term called beta, which is defined as alpha over 1 minus alpha. I'll explain what these terms physically mean, but let me just complete this because when I have numbers, it's easier to explain. So 0.055 times it should be 19. Okay, the value of beta is 19. Fine. This is you can at least you can it's fairly simple to understand. So let me draw this BJT now. N, P, N. So N plus just to denote the emitter side. And please remember, we are operating in forward active mode. So this terminal must be forward bias. This junction, forward bias, emitter base. And this one, the base collector should be reverse biased, right? So I believe I have done it correctly. Yeah. So this is VBE and this is your VBC, let's say. Okay, and IE, one second. Just a second, I'm making some mistake. No, okay, fine. So yeah, from positive terminal, yeah, it's correct. It comes something like this and it will like this. So this is IC, this is your IB, and as I've told, if you ignore the reverse saturation current, this will be nothing but ICN, right? This ICN. So alpha, which you see this term over here, is nothing but your collector current to the emitter current. There's no ICP here because again, please remember, we are ignoring the reverse saturation current, which is very fair assumption because its magnitude is much smaller as compared to the typical numbers that we see. Even the previous problem you saw, the currents that we are seeing, IC, IE, IC, were in milliamps, right? And this reverse saturation current is usually in picoamps or something. So that's a fair assumption to ignore that. Alpha is nothing but, so to speak, is your IC over IE. Beta is coming out to be 19. That's a numerical number, that's fine, but what does it denote? So let's see that. Essentially, beta is it's also known as your current gain. I'll use a different color for the analysis, but this is our current gain given by IC over IB. Let's try to see if it's true or not. So alpha was ICN over IE divided by 1 minus alpha. So this will be ICN over IE divided by IE minus ICN over IE. IE gets cancelled. What we are left behind is ICN divided by IE minus ICN. Now remember Kirchhoff's current law, that IE, I'll write it here, IE will be nothing but ICN plus IB, right? So IE minus ICN would be what? IE minus ICN will be nothing but IB. So this is ICN over IB. Again, ICN is equal to IC. That's what I've written here. This term is of primary importance, in fact, in the forward active mode. So all these parameters like emitter injection efficiency, base transport factor, which their multiplication gives us alpha, which in turn we can use to obtain beta, the current gain. So this finally we are only concerned about beta. So for instance, if circuit designer may not worry much about what is the emitter injection efficiency or base transport factor, they'll say, okay, beta is this much and this is the maximum bias voltage that I can apply, and so on. They'll design their circuit according to that. So this beta is of primary importance, the current gain. And remember, when you're talking about amplification, I told that when you're at forward active mode, we are this in this region, when the device is biased such that it's in forward active mode, we use for amplification purposes. You can see that here. If IB is, let's say, if I'll take a realistic estimate. So let's say for some problem, IB is given to us at 1 microamps. Okay, right. So what will be IC in that case? So IC will be beta times IB. The value of beta is, again, let's say in this problem it's at 19. Usually beta can be higher, 100, 80, 90. That's the typical numbers that you encounter. So it will be 1 microamps. So what you have done is that you have boosted the input current, which was 1 microamps, to the output current, which is 19 microamps. That's the amplification we are talking about. Usually there is a load resistor there. We measure the voltages across that in terms of amplification. Sometimes just to drive home the point, just to keep it simpler, just I gave this example. Okay, so these 4 terms, just to capture the summary for let's say a discussion of last 15 minutes or so, the 4 terms that we saw: emitter injection efficiency, base transport factor, alpha, and beta. So these 4 terms are they determine, in fact the first 2 terms rather, gamma E and B, base transport factor, determine alpha and beta. But when you're using problems, you'll very often circuit problems will not see gamma E and B. You'll see alpha and beta there. So you must remember where they're coming from. There's some physics behind that, which like gamma E, injection efficiency, and so on. And those are the terms which come into which are finally the parameters that we use is alpha and beta. Okay, so that's about that. Now the discussion will be more or less straightforward, because I have discussed these things in quite a bit detail, that how they work essentially. So now it's just an thing of application now, what our understanding is still now. So we have 2 BJTs in this problem, A and B. The base doping of A is this much. So base doping, you can see, is ND. This means it's a PNP, because base doping is donor type. Okay, so let me first draw that. Okay, let me first draw that. So this is P plus N and P. Okay, and this is our first BJT A. The second device we have it's the same. It's also a PNP, because you see ND written here. So we have device P, again P plus N and P. This time NDB here is given as 5 into 10 to the power 17 per centimeter cube, while for the first device we had where is it, 5 into 10 to the power 16. So NDB here is 5 into 10 to the power 16, okay, per centimeter cube. The other parameters are the same. That means your the acceptor doping NAE1 equal to NAE2, and the geometrical parameters are also the same, which is written over here. So in terms of geometry and doping, everything else remains the same. Okay, now which of the following statements are true assuming identical emitter injection efficiency? Okay, fine. We'll assume emitter injection efficiency to be the same. First thing that we need to analyze, again, more than one option may be correct. Okay, first analysis regarding the base transport factor. So let me first write the expression for the base transport factor. Okay, so base transport factor, I'm calling this BA for this device A here. So BA would be is ICPA, that means for device A, divided by IEPA. Okay, yes, that is correct. And so what we now need to now the thing that we know is that they have the identical emitter injection efficiency. Okay, So what that means is, let me try to figure this out over here. So gamma E is same for both of them, and gamma E is IEP. Remember, this is a PNP, IEP plus IEN. So this is the same for both of them. Okay, what I can now simply assume is that now IEP, please remember, now IEP, if you recall, is directly proportional to is inversely proportional to rather n, the doping of the base. So in this case it is NDB. So IEP is inversely proportional to this. Okay, and IEN similarly on the other hand is directly proportional to NAE. This is a P type, so M except a doping in E type. Okay, but if their injection efficiencies are the same, yeah, but if their injection efficiencies are the same, correct. So we are dealing only in terms of the ratios. Okay, fine. Now it's not so much of a numerical analysis than so base transport factor here will be ICPB over IEPB. Okay, what I'll do, I'll make one based on the assumption that we are given that gamma E A is equal to gamma E B. I'll claim that the amount of holes that are reaching here as well as here are the same. Okay, I know the NDB is different over in that case, in fact one order different. So IEP, but it's the base transport factor, essentially is the ratio that matters, not the absolute number. But base transport factor, what I'll claim now this is that base transport factor depends on the number of recombinations. This implies if base doping is high, recombination will also be high, right? And what you see is the value of B should decrease. So among these two fellows, A and B, the base doping of B is high, 510 to the power 17, one order higher. But this means that whatever holes are being injected in both the cases, the more recombination will happen here. So here what will happen is, use same color rather. I'll continue with this, sorry. So more recombination for BJTB. This is our final response. So I can say now that BA will be greater than BB. Base transport factor will be higher in A than in B, and I'll simply multiply it by gamma E, which is the same for both of them. Let's say this is equal to gamma E. So gamma E times BA must also be equal to gamma E times BB, right? And this is nothing but alpha, right? This is nothing but alpha. So alpha for A will be greater than alpha for B, and if alpha is larger, beta will also be larger. Just put in that expression, alpha upon 1 minus alpha. You will arrive at that. So if essentially what's happening is that now in BJTB, more of the holes that are coming from the emitter are getting recombined. So naturally, lesser amount of them will be able to drift across the collector and reach the final battery terminal. So naturally there will be much lesser current, right? So what we have is that base transport factor of BJTB is less. BJTB is because there is a more recombination, and consequently beta for A will be larger than beta of B. This is alpha of A is also larger than alpha of B, which gives me beta of A is larger than beta of B, It's straightforward. All right. So this was a good problem. Again, we had to switch from NPN to PNP first of all, and secondly, the base transport factor, as I told, is dependent on doping of the base, which in this case we saw clearly. The doping is higher, more recombination, so base transport factor will reduce, and alpha will reduce thereby, because emitter injection efficiency has been given the same, right? So that will reduce, and yeah, so that is all. This part is essentially of no use. IEPA equal to IEPB, because I mean, we are simply multiplying gamma E, so that was of not much significance. The absolute values of current, we did not encounter them. That's why I was just thinking whether I can get into some absolute number of absolute current, but that was not required. In fact, the ratio that is important. So that's that. Okay, right. So the next problem that we have is, consider the base collector junction of a BJT operating in forward active mode. So it's been given forward active mode, assuming base doping does not affect the EB junction operation. So that means even if you change the base doping, your so I'll say, what do I mean? So this is N plus P and N. So this is emitter, base, and collector respectively, right? So we are in forward active mode, so this means this is forward bias and this is reverse bias. Okay, VBE, VBC. Now, what in this problem we are changing the base doping. Okay, so we need to analyze, if we change the base doping, what happens. So it's saying that assume base doping does not affect the emitter bias junction. This means the currents that are the electrons that are injected here, they will not change, right? The amount of electrons, so emitter injection efficiency, they're saying is not does not impact that much. Okay, so since EB junction performance remains same even after we have to decrease the base doping, even after decreasing base doping, gamma E must remain the same. That is the term that we are concerned about, must remain same. That's the assumption that have been given. But since NAB, this is P type, so acceptor doping in base has reduced, recombination must reduce. In other terms, base transport factor should increase, right? Because lesser recombination, the same problem we have, same principle we have discussed in the last problem. So what this would mean is that now if base gamma E, so alpha is gamma E times B, this does not change, this increases, so this must imply alpha must increase. Alpha increases, gain, which is beta, it will also increase. Simple as that. Essentially you can see that since emitter side it's not changing, the action is happening only in base. So lesser electrons will recombine, which are coming from the lesser amount of electrons which are coming from this to this are recombining over here. So most of them will reach there. So essentially the gain is increasing. The gain is IC over IB. So that will also increase. Okay. Decreasing the base doping increases the gain. So that was a straightforward problem rather. Okay. So I think I should have 1 or 2 more problems. I have 10 minutes. I think we should be good. Okay. So you are given 2 NPN BJTs, one made of gallium arsenide, it's known as sample X, another gallium nitride, sample by both are NPN. Consider room temperature situation. Devices are separately operated under forward active mode. Very good. The gain of the samples, this is the current gain, that is IC upon IB, or both of them have been given as this. What we are required to do is that now we have to shine light Okay, so what does happen when we shine light? So first we are shining light of 520 nanometers. So let me first just convert it to the what corresponding energy this is. Okay, so if you recall the expression 1.2 over lambda in micrometers, right? This was I think last session or last to last. So 1.2, it's 0.52, this is nanometers, so convert it 0.52 microns. So this will coming out to be 1.2 over 0.52, around 2.3. So this number is 2.3 eV. So shining a light which has energy 2.3 eV. So what this will do is that when you shine 2.3 eV on GaN, nothing will happen. See, when you're shining light, essentially it generates electron hole pairs. That's what's happening. Okay, when you shine 2.3 eV energy light on GaN sample, nothing will happen because its band gap is 3.4 eV. This is sample Y GaN. This is 3.4. Even if an electron that is here, if you shine 2.3 eV light, it can go only here, and there is no state that is present here. So this photon is useless. Okay, so at least on GaN it will not impact at all, and this is the ideal case we are considering. So there are no irregularities like there suddenly there are some trap states also there, realistically, but we are not considering that here. So for as far as so for GaN it will not do anything. So this option is wrong, false rather. So yeah, so this is wrong. This option is, this is correct, this is correct, and this is correct. Fine. So second is that when beta x increases when the quasi-neutral base region of sample x, when the sample x is illuminated by this. So sample x gallium arsenide has a band gap of 1.4 eV. When you shine a light of 2.3 eV, naturally what's going to happen, we are shining the in the base region, quasi-neutral base region. So which one is that? So n plus P and N. So these are the depletion widths, let's say. This region, WBN, neutral base width. We are shining light in this region. Okay. Right. So you're shining light over here. Right. So now let's see what's going to happen. So now what we can clearly see is that if you're analyzing the option B, electron hole pairs will be generated, right? But where will they go? There's no electric field here. They'll essentially recombine. Beta cannot increase. See, beta, if you recall, beta will now is alpha over 1 minus alpha, and alpha is gamma E times your base transport factor. So gamma E will be determined when something changes on the base emitter region. Nothing is happening. We're shining light in the quasi-neutral region, right? So this is not impacted, unchanged. Base transport factor, will the recombination increase? Yes, recombination will increase because now there are many more holes. Some electrons which are coming here, they'll see many more holes. But the electrons are also generated here, right? So essentially, it will be the net effect will be 0. The electron hole pairs will be generated and they'll recombine. So B will also remain unchanged. Thus gamma will remain unchanged. Beta x will also remain. We have already seen GaN does not get impacted with shining of this light. So beta x will not increase. So this option is also false. So this is there. So this option is also eliminated. Option C. Beta x does not change when the quasi-neutral base region. This is what I just talked about. So this is true. So this is true, this is false, this is false, this is so technically I think this is the correct option. But let's also analyze the option D. Beta x does not change when the quasi-neutral emitter region is illuminated. Okay, so now in this case, so this was the case for option B and C. Now for option D, what we are doing is we are shining light N plus P and N. We are shining light here. This will generate electron hole pairs, and please remember this is connected to some external battery. It's positively charged. Essentially what you're doing, you're injecting more electrons, right? That's what you're doing. So this will impact because this will generate, now more electrons will be generated here and they'll diffuse across through this region and they'll contribute. So essentially you are it's saying something like when you're increasing VBE, rather than increasing the potential of the battery, you're just shining light, electrons will be generated more. So that's that. So beta-X will change, in fact beta-X will increase. So this is false, so this is incorrect. Yeah, so again option B will be the correct option. This was a good problem because till now we have been talking about in NP and BJTs the effect of only voltage, but it doesn't matter where the carriers are coming from, through light or through voltage. So that was this is a good illustration in that. All right, so as I've been saying that we have not we did not see any problems till now where BJT was used in a circuit. So you might encounter such certain problems where, let's say, BJT is used in a circuit. So for instance, one rather simple thing is like this. This is VCC, this is, let's say, 10K, this is let's say 5K, this is grounded, and this is connected to again one more resistor 100K, and let's say this is connected to some VB. All right, and we are taking the output from here, and you are required to find the output voltage over here, let's say the current through this load resistor. In such kind of problems where BJT is employed in a circuit, as I told you, there we do not care much about what is gamma E or base transport factor. There you will be given some alpha and beta. So there you will employ these, and these are some things that you may consider, that VBE is 0.7 volts, VC SAT is usually 0.2 volts. If these are some typical numbers that are given for silicon based NP and NPNP BJTs. This is just a slide that I just put it because you might, I don't know whether you have problems in the current assignment based on such problems or not. Sorry. Okay, so last problem for today. I have got a couple of minutes, that's all. So in this problem, consider two BJTs A and B with identical designs in forward active mode, very good, and operating as common emitter amplifier. They are being operated as an amplifier, and we have been given that the current for is 20 milliamps and ICB is given as 40 milliamps. So we are required to find which has better voltage gain, and voltage gain is given by this expression, GM times R out. R out is the same for both of them, right? So that doesn't matter. So only parameter that matters is GM. So what is GM? GM is output differential of output current divided by the input voltage. Transconductance. Conductance is voltage over current. Sorry, current over voltage. Trans means from the other side. So output current over input voltage. Okay, what is the output current? We know that IC is approximately equal to IE, right? So what we do know is that I can write that is that IE over del VBE, and IE I know is some I naught e to the power q VBE over KT del VBE. I naught is a constant that comes out. We differentiate this term, so e to the power kx is k times e to the power x, so this will be q by KT, and what we have is so we'll get del VBE over del VBE. This is 1. So what I get is I naught, the exponential term will also come out, e to the power q VBE over KT. So I naught q VBE over KT over KT by q. This term is nothing but your IC again, so IC over KT by q. So GM, the transconductance, is nothing but IC over KT by q, simply. So GMA will be ICA over KT by q, and GMB will be ICB over KT by q, and as we know AV, the voltage gain, is GM times R out. So AVA will be ICA over KT by q R out, and AVB will be ICB over KT by q R out. This is ICB. sorry, this is AVB, not ICB, sorry about that. This is AVB. So this is the, yeah, okay. So R out and R out are the same, KT by Q is the same. ICA and ICB are the only factors that determine the voltage gain, and we know ICB is 40 milliamps, ICA is 20 milliamps. So we can say since ICB is greater than ICA, this implies AVB will be greater than AVA. So voltage gain for BJT-B will be higher than BJT-A. So this is the correct option. This is more based on the small signal analysis, as I've been saying. I have one video, not couple of videos, regarding the small signal of analysis of a BJT. If you are interested, I'll put that link in the description as well as at the end of the video. If you are interested, just go through that. As far as this session is concerned, it's done from my side. Thank you for listening. Thank you for staying back.